Fractal geometry is the underlying cosmological principle. But what exactly do I mean by fractal geometry? What is a self-similar pattern? And what do I mean when I talk about fractal dimensions? To understand this, let us look at a simple example, the Koch snowflake, whose construction is predicated on a simple recursive algorithm. The Koch snowflake can be constructed by starting with an equilateral triangle, then recursively altering each line segment as follows. First, divide the line segment into 3 separate segments of equal length. Next, draw an equilateral triangle where the middle line segment is the new triangle's base with its tip pointing outwards. Then, lastly, remove the line segment that is the base of the new triangle. Thus, after one iteration of this process, the resulting shape is the outline of a hexagram. Repeating this process iteratively renders the Koch snowflake. So, for the next iteration of this procedure, again, divide the line into 3 separate segments of equal length. Then, draw an equilateral triangle with the middle line segment acting as the base of the new triangle with its tip pointing outwards. Lastly, remove the middle line segment to complete the second iteration of the Koch snowflake algorithm. And as we proceed through all the other iterations, the fractal curve that is the Koch snowflake comes into view. A self-similar object is exactly or approximately similar to a part of itself. The self-similar pattern of the Koch snowflake is seen by taking one of the lines and dividing it into 4 parts, each part an exact copy of each other as well as a scaled down copy of the original whole. The length of each of the 4 parts is 1/3 the length of the original whole. The concept of a fractal dimension is defined by the duality in this division of the whole between both the length and scale. This dual concept in the division between length and scale is most easily seen in considering a line, a square, and a cube. A line can be divided equally into 2 new lines, each line a copy of its original, scaled down by a factor of 1/2. A square can also be divided into 4 new squares. Each of these 4 new squares is an exact copy of the original square, again scaled down by a factor of 1/2. A cube can be divided into 8 separate cubes, each an exact copy of the original, but again its size is scaled by a factor of 1/2. This division into exact copies of the original, whereby each copy is scaled by 1/2, is done by length. Another way of looking at the scaling process in order to produce exact copies of itself is by mass. Imagine our line is a piece of wire that is cut equally to produce 2 new pieces of wire, each of equal length to one another. The mass or weight of each of the 2 new wires is 1/2 of the original whole. However, for a square sheet of metal divided into 4 squares, the weight and surface area of each square is 1/4 of the original, and for a cube of metal divided equally into 8 cubes, the mass and volume of each is 1/8 that of the original cube. So we can say that when we scale down the length of the line by 1/2, the mass of the line is in turn scaled by 1/2, or 1/2 to the power of 1, as in one-dimensional is equal to 1/2. Conversely, when we scale down the length of a square, the mass of the square is scaled by 1/4, or 1/2 to the power of 2, as in two-dimensional is equal to 1/4. And when we scale down the length of a cube by 1/2, the mass of the cube in turn is scaled by 1/8, or 1/2 the length scaled to the power of 3, as in three-dimensional, which is equal to 1/8 the mass scaled. It is in the to the power of relationship, equating the scaling factor of length to the scaling factor of mass, that the concept of what is meant by a fractal dimension is given definition. So for a 2-dimensional square, when its length is scaled by some factor, then the resultant mass or weight is equal to the length scaling factor raised to the power of 2. And for a 3-dimensional cube, when its length is scaled by some factor, then the resultant mass or weight is equal to the length scaling factor raised to the power of 3. It puts the 3 in 3-dimensional. Returning to the co-snowflake. Here, the pattern of the whole is equally divided into 4 parts, each of which is an exact copy of the whole. The length of each of the 4 parts is 1/3 of the original whole. Hence, we can say it is scaled in length by 1/3, but scaled in mass by 1/4. Its fractal dimension d is 1/3 raised to the power of d such that it equals 1/4. Applying logarithms, we see that d is equal to around 1.262. Hence, the fractal dimension of the co-snowflake is equal to 1.262. Let's look at another simple fractal curve, the Sierpinski triangle. Here, when the Sierpinski triangle is scaled in length by a half, it renders 3 copies of the original whole. Here, the length is scaled by a half, and the mass of each of the 3 parts is 1/3 that of the whole. So, its fractal dimension d is 1/2 to the power of d such that it equals 1/3. Using logarithms, we see that d is equal to around 1.585. Thus, we say the fractal dimension of the Sierpinski triangle is 1.585. As a rough analogy, the measure of fractal dimension can be viewed as a measurement of how rough a given curve is. This analogy is best seen when applied to the real-world problem of measuring the length of a given coastline. Take a coarse grid with the coastline of Britain drawn upon it and count the number of squares touched by the British coastline. Next, zooming in onto the coastline of both England and Wales, repeating the same process, counting the number of squares touched by the coastline. Zoom in again and repeat the same box counting process. What we find is the number of boxes touched by the coastline is roughly equal to a constant multiplied by the scaling factor to the power of 1.21, which is the fractal dimension of the British coastline. A curve is said to be fractal if this relationship holds for any scale. In the case of the British coastline, this has been shown to be the case where the fractal dimension is equal to 1.21. A rougher coastline, like Norway, has a fractal dimension equal to 1.52. Another example from nature is the surface of the sea. A relatively calm sea has a fractal dimension roughly equal to 2.05. This is in contrast to a stormy sea surface whose fractal dimension is roughly equal to 2.3. The larger the number, the rougher the fractal surface or curve actually is. If our universe is indeed fractal, then what is its fractal dimension? Maybe its value is to be found when considering lambda, the cosmological constant. Possible, but the first step here is to try and identify the shape of the self-similar pattern from which the universe and beyond is formed.